So in the previous lecture we saw the transients in transmission line, but in that case we took a constant voltage source, right? So we did not take the impedance of the voltage source. Now we will consider the impedance. Okay, so we will discuss 2 points here. One is the loaded synchronous generator and the other is the non-loaded synchronous generator. Okay, so first we are going to see the short circuit of synchronous generator at no load. Okay, so why we are considering the synchronous generator here? Why not some other generator? In power systems we use the synchronous generator for power generation. Okay, so this is often also called as alternator. Now we will discuss a bit about the reactance. The reactance is going to be different at different instants of time after the fault occurs. Okay, so we will see why it is different and what will be the value. Reactance of alternator is different at different instants of time after fault occurs. First type of reactance is one which occurs immediately after the fault. So this is called as subtransient reactance, and this is represented as XD double dash. Okay, so you can draw the impedance something like this. Here we take a switch, okay, and the switch will be closed at the instant when the fault occurs. Okay, so we are not considering the resistance as of now. This is because the value is low in comparison to the reactance. Okay, so now this entire thing is called as XD double dash. So what are these individual reactances? The first one here is XL. So this is the leakage reactance, and here you have the reactance due to the damper winding. Next you have the reactance due to the field winding, and finally the reactance due to the armature. Okay, so immediately after the fault occurs, what is going to happen? The current is going to flow through the field and the damper winding. So that's why they come into picture. Okay, and they will be in parallel to the armature winding. So that's why we represent the reactance in parallel. Okay, so immediately after fault occurs, current appears in field and damper winding. Now what will be the expression for subtransient reactance? XD double dash is equal to XL plus XDW in parallel to XF in parallel to XA. Okay, and what about the fault current? So here we are taking IF double dash, and similarly we have taken EG double dash here. So this is all during the subtransient period. So you can write it here, subtransient period. Okay, so what will be the fault current? This is going to be equal to EG double dash by XD double dash. Okay, so EG double dash, it can be found from the pre-fault condition. When we discuss the loaded case, it will become clear how to find the pre-fault condition. So this is the subtransient internal voltage of generator. The next is 3 to 4 cycles after fault occurs. So this is called as the transient reactance, and this is represented as XD dash. Here the damper winding reactance is going to be not there. Why? Because the current through damper winding is going to decay faster, at a faster rate. So the circuit is going to be something like this, only two reactances in parallel. This is the leakage reactance, the field reactance and the armature reactance. Now the fault current here is the transient fault current IF dash, and here you have the transient internal voltage. So this is the transient period. Previously it was the subtransient period, right? So here time constant of damper winding is much smaller. So current in damper winding dies out faster. So the transient period is the time wherein only the reactance due to field is left out, while the reactance due to the damper winding is not present anymore, right? So this is going to be, the transient reactance is going to be the leakage reactance plus the field and the armature reactance in parallel. And what about the fault current? Transient fault is equal to Eg dash by Xd dash. This is the transient internal voltage. Okay. And finally we have the steady state. So this is the steady state reactance, which is called as the synchronous reactance, represented as Xd. Okay. So this will occur after a few more cycles. So basically the current in field winding also will die out. That period is called as the steady state period. Okay. So the circuit is going to be like this. Here you have the leakage and the armature reactance. This is called as the steady state period. And now the fault that we have here is the fault current IF, steady state fault current. Okay. So what is the synchronous reactance? This is equal to XL plus XA. So here you can write this point as well. After a few cycles, current in field winding also disappears. Okay. And the fault current, the steady state fault current, previously it was the transient fault current, and before that it was subtransient fault current. So now the steady state fault current IF is equal to Eg by Xd. Now if you see in these three of the cases, in the steady state here you have XA, and in the transient part you have, in addition to XA, you have XF in parallel. So this entire reactance will be lesser than XA, right? So this entire reactance is going to be lesser as compared to synchronous reactance. So the fault current will be more. And similarly further in subtransient period, what is going to happen? This damper winding reactance will also appear in parallel. So this reactance will further fall, right? So this fault current is going to be much higher. Okay. So in this manner we will get a relation which current is the highest, the subtransient fault current is going to be higher than the transient fault current, which is going to be greater than the steady state fault current. Okay. So this is one important observation, and this is because the subtransient reactance is less than the transient reactance, which is less than the synchronous reactance. So this is the short circuit of synchronous generator under no load condition. Next we will see the case of short circuit of loaded synchronous generator. Okay, so here the load that we are going to take is a motor, synchronous motor. Okay, so the circuit is going to be like this. This is the reactance. Under normal conditions, this will be the reactance. So here I have taken the subscript G to denote that it is the synchronous reactance of the synchronous generator. Okay, and here this will be the internal voltage Eg. This is the impedance of the transmission line, and from the transmission line it is connected to the load, which is the synchronous motor. So this reactance we are going to take Dm, subscript Dm, and this is the internal voltage. Okay, this is under normal steady state condition. Okay, that means no fault has yet occurred. So the load current we will take as IL. Now we will see what will happen when short circuit occurs. Let us say the fault occurs at a point P here. Okay, so fault occurs at P. Now as soon as the fault occurs, what is going to happen? These values, this internal voltage will become subtransient internal voltage, reactance will also become subtransient reactance. Here also this is a synchronous machine, right? So here also subtransient values will take over. Now in order to be able to calculate this subtransient internal voltages, we will make use of two circuits. One is the pre-fault circuit and other is the post-fault circuit. So the pre-fault circuit, it will have no short circuit, but all of these values will be subtransient values. Okay, so let us say the current that was flowing was still the load current IL, because fault is not yet taking place. So this is point P. This is the subtransient reactance. So subtransient internal voltage of the synchronous motor. Okay, so this is the pre-fault circuit. What will be the post-fault circuit? Here there will be a short circuit. Right here now the fault current is going to flow, and this will anyways be the same thing now, EM double dash JX DM double dash. Okay, so this is the current from the generator. So we will take it as IG double dash because it is the subtransient current, and this is going to be the subtransient current from the motor. So from here we can write the equation. This voltage we will take as VF. Okay, now EG double dash you can write as this is equal to the drop across this and this reactance and VF. So EG double dash is equal to VF plus IL into JX DG double dash plus Z. This is one equation, and second equation is the internal voltage, subtransient voltage of the motor. So this is equal to VF minus JXDM double dash IL. This is the second equation. So what we did is we have expressed the subtransient internal voltages in terms of VF and IL. Okay. Now similarly you can write the equations for the post fault circuit. Okay. So what we want here, we are concerned with the fault current. So this fault current here, it will be the subtransient fault current. So double dash. Okay. So what will be IF double dash here? This is equal to IG double dash plus IM double dash. Now what will be IG double dash? This is going to be, if you take this circuit, right, this is one loop. So the current through this is going to be EG double dash divided by this impedance, reactance. Okay, and similarly IM dash you can write as EM dash divided by this reactance. Okay, so here you can write EG double dash divided by Z plus X DG double dash plus EM double dash divided by JX DM double dash. Now you have these values EG double dash and EM double dash from here. Okay, so if you are going to substitute here, then the final value of the fault current that you are going to get is, substituting Eg dash and Em dash values from equations 1 and 2. We get something like this: If double dash is equal to Vf by Z plus Jx dg double dash plus Il plus Vf by Jx dm double dash minus Il. So what will happen here? This Il and minus Il, they will get cancelled. Okay. So this entire part is the current from the generator, which is Ig double dash. This entire part is Im double dash. Now what will be left out? Vf by Z plus Jx dg double dash plus Vf by Jx dm double dash. Okay. So this part here, this we often write as Igf double dash. Okay. So this is the fault current contributed by generator. Okay. And note that this is not the same as the current flowing from the generator. Okay. So this is not equal to, sorry, not equal to. Okay. And similarly this is represented as Imf double dash. So this is the fault current contributed by the motor. Here also Imf double dash is not equal to Im double dash. Okay. Similarly, this is the subtransient fault current, right? Similarly, you can find the transient fault current. So wherever subtransient values you have taken, here instead of Eg double dash you will take Eg dash, and here x dg dash you will take. All the transient values you will take. You will get the similar expression. So we obtained the fault current, the subtransient fault current, as Vf divided by Z plus Jx dg double dash plus Vf by Jx dm double dash, right. So Vf is the pre-fault voltage at the point where the fault is occurring. Okay. So now this you can write as Vf into 1 by Z1 plus 1 by Z2. Okay. So what are Z1 and Z2 here? Z1 is equal to Z plus Jx dg double dash and Z2 is equal to Jx dm double dash, right. So if you are taking Z1 and Z2 in parallel, right, then what will be Z equivalent? It will be related to these two as 1 by Z1 plus 1 by Z2 is equal to 1 by Z equivalent, right. So this entire thing you can write as 1 by Z equivalent. Okay. So this is nothing but Vf by Z equivalent, where Z equivalent is the equivalent impedance when Z1 and Z2 are connected in parallel like this. Okay. So from here you will be able to get a circuit like this. You have the voltage Vf and here you have Z plus Jx dg double dash Jx dm double dash, and the current that is flowing here is the fault current. Okay, subtransient fault current. Now what is the importance of this kind of approach? If you see through this, what will be the equivalent Thevenin impedance we will take? Okay, because this is the Thevenin's approach that we are going to discuss. So Z Thevenin's is Jx dm double dash in parallel to Z plus x dg double dash. Okay, and now if you consider the fault circuit, in the fault circuit you have the subtransient values, the subtransient internal voltage, impedance will be as it is of the transmission line, and this is the subtransient value of reactance of synchronous machine. Similarly, internal voltage. Now this is the point of fault, right? This is where the fault is occurring. Now if you look through P, okay, so if you are looking through P, what will be the Thevenin's impedance? In Thevenin's impedance you have to short the voltage sources, okay. So if you are shorting it and seeing through the fault point, then you are getting the same Thevenin's resistance as this, okay. So this is same as this. So from here you can see that we can get an easy approach, okay. So what is that? First find out the pre-fault voltage Vf, okay, and second is find Thevenin's impedance looking through the point where fault occurs, okay, and now find the fault current from following circuit. So what is the circuit? It is going to have the pre-fault voltage Vf and the Thevenin's impedance that we found out, okay. So this you can take, this is Vf, we know already, and this is Zth. So using these two parameters we construct this circuit, and we are going to get the fault current simply as Vf by Zth, okay. So this is the working model. This is how we are going to find the symmetrical fault currents. So this is If double dash here.